Cavitation is the term given to the formation and collapse of cavities in liquid. Over 100 years ago, cavitation was recognized but not clearly understood. In 1894, the eminent scientist Osborne Reynolds made the following contribution to a meeting of the British Association.
Amongst the many phenomena, the secrets of which have been preserved by the deadening influence of familiarity and curiosity, there is perhaps none more remarkable than the singing of the kettle on the hob, which has many times been subject to sentiment and doubt, but not, it would seem, hitherto a subject of physical study. At about 10 degrees below the boiling point, a harsh hiss comes on suddenly, and in a glass vessel it may be observed that simultaneous with this sound there appear bubbles at the bottom of the vessel, which grow gradually until they start to rise, when, unlike bubbles of earth, they suddenly collapse with a sharp click, which, being rapidly repeated, causes a sharp hiss. The reason of the collapse of these bubbles is that they are bubbles of steam at the temperature of the boiling point at the bottom of the vessel, formed on the surface of the glass and held down by capillary action until they are large enough to break away and ascend, when their ascension brings the steam into contact with the colder water above. When being free from earth, their collapse is sudden and sonorous.
The severity with which steam cavities collapse can be seen when a test tube of water bumps vigorously as it nears the boil. Temperature variations alone create and collapse steam cavities in near boiling water. Similar vapor-filled cavities can be created in a liquid at normal temperatures. Without the influence of temperature, the reciprocating motions of the plunger in this syringe create and collapse vapor cavities or cavitation in the liquid, and this is due solely to variations in pressure. The way that these pressure variations arise can be followed in this diagram of a Venturi Meter, a device used to measure fluid flow. Liquid is caused to flow through a convergent-divergent tube. The energy of the liquid in the Venturi must remain constant at all points. Thus, as the velocity increases in the throat, so the pressure must decrease, rising once more to the original value as it emerges from the throat. When the minimum pressure is low enough, vapor cavities are formed. As these pass into the region of rising pressure, they collapse. If the rate of pressure rise is high, then their collapse is violent. In a single cavity, or hole in a liquid, it is seen that the liquid alone encloses the cavity. The amount of vapor in the cavity, depending on liquid temperature, determines the force with which the liquid interfaces come together. Low temperatures give little vapor and large forces. High temperatures, more vapor to cushion the blow. See what happens when a Venturi restriction is placed in the flow of water from a laboratory tap. As the water flow is increased, vapor cavities are seen forming at the Venturi. Any solid surface near to this cavity collapse for a reasonable period of time will be damaged by the myriad hammer-like blows of cavitation. In engineering practice, the lubricant film in journal bearings is subject to pressure variations. This model has a plain journal dipping into a bath of lubricant, a plastic half bearing with manometer tubes to show pressure distribution, and a weight with which to load the bearing. As soon as the journal starts to rotate, pressure is built up in the lubricant film as indicated by the manometer tubes. It is seen, however, that the extreme right-hand tube shows no pressure. It is in fact situated over a negative pressure area of the bearing surface. Air is being drawn down the tube and can be seen as a distinct splume between bearing and journal. By preventing air from entering at this point, conditions inducive to cavitation could arise. This is an actual bearing that has failed in service due to cavitation. Unlike other forms of bearing failure, it is seen that this damage is very localized. Now we shall examine cavitation effects in liquids that are not restricted in their flow. A metal specimen is screwed into the base of a high-frequency oscillator, and then the specimen is immersed in the liquid under test. The oscillator is switched on and tuned. The specimen vibrates rapidly against the liquid. By arranging that the surface of the specimen can be seen, it is possible to observe vapor cavities forming and collapsing. In a short space of time, extensive and distinctive damage takes place on the metal surface. You will now see a series of distinctive damage patterns produced by different liquids on uniform metal specimens in this cavitation test rig. That such extensive damage can result from the collapse of minute vapor cavities is difficult to realize until it is appreciated that the liquid interfaces, on collapse, approach each other at several hundred miles an hour, generating forces of many tons per square inch. Precise figures for these immense forces depend on liquid temperature, since the higher the temperature, the greater is the amount of vapor in the cavities to slow down the collapsing liquid interfaces. This vibration-induced cavitation is also found in engineering practice. A cylinder liner vibrates like a bell when struck with a hammer. The cylinder liner of a running diesel engine can vibrate in the same way due to the alternating forces set up by combustion of the fuel. The water side of the liner will vibrate against the cooling water, and this can cause cavitation of the metal. In close-up, these sections cut from a cylinder liner show the extent of damage on the cooling water surfaces. So far, it has been possible to describe the conditions necessary for the formation and collapse of vapor cavities in liquids. Two examples of cavitation in engineering practice have shown that metal surfaces are easily damaged. Now we will consider the rather different situation that arises when vapor cavities are present in a fluid used as a power transfer medium. A common example of this is found in hydraulic systems, where the fluid transfers power as well as being the lubricant for the pressurizing pump. The demonstration hydraulic pump has a new cartridge assembly, and so that we may see inside, it is fitted with special transparent components. As the pump starts running, a strobo flash lamp is switched on and set to give one flash to each revolution of the pump. In this way, the rotary movement of the pump components is nearly arrested, allowing detailed observation in slow motion. It sometimes appears that the pump rotates clockwise. This is not so, and in all cases it rotates anti-clockwise at 1440 revolutions a minute. In order to induce vapor cavities in the fluid, the pump inlet is restricted with a gate valve in the fluid sump. As the valve is closed, a negative pressure shows on the manometer connected to the pump inlet. Soon a point is reached where vapor cavities can be seen entering the pump through the transparent inlet pipe. With the slow motion effect produced by the strobo flash lamp, we now move into the heart of the pump. At first, nothing unusual is seen. But as the valve continues to restrict the supply of fluid to the pump, vapor cavities are seen forming in the inlet ports at the 4 o'clock and 10 o'clock positions. Each pumping enclosure, that is, the space between adjoining vanes, moves with its mixture of fluid and vapor cavities, still under negative pressure, round towards the outlet ports at the 2 o'clock and 8 o'clock positions. During this movement, the presence of vapor cavities in the fluid impairs lubrication between ring surface and vane tip, allowing metal-to-metal contact and scuffing of the ring surface. As soon as a pumping enclosure reaches an outlet port, its contents are suddenly subjected to high pressure, collapsing the vapor cavities and causing cavitation damage to the flaps of the vanes. In addition, the vanes are agitated violently in their grooves. The tips strike through the lubricant film, creating wear steps on the ring surface. Move in closer and watch this again in slow motion. The inlet port is full of vapor cavities, but the outlet port is clear, since all the cavities have collapsed due to the high pressure at this point. Vapor cavities in the fluid have impaired effective lubrication, the ring surface is badly worn, the vanes are damaged, the vane grooves in the rotor are worn, and the bushings show wear in the area of contact with rotor and vanes. Severe wear steps are found on the ring surface in the immediate area of each outlet port. The surface between inlet and outlet ports is damaged by scuffing wear marks. The flat of this vane shows typical cavitation damage, whilst the tip shows severe wear marks due to incomplete lubrication. The pump is now fitted with a badly worn ring, and it is possible, once again in slow motion, to watch the vanes leaping off the wear step at the outlet port on the right. As each vane lands back on the ring surface, it does so with considerable speed and impact, breaking through the lubricant film and promoting wear. It is evident that vapor cavities can be formed in a liquid, either flowing or static, that is subjected to negative pressure. Collapse of these cavities can damage metal surfaces, and their presence in a fluid that has to lubricate will reduce effective lubrication. In the same way that the heart of the hydraulic pump is now hidden, so it is with our other examples. We cannot always see cavitation happening. Perhaps we may finish with another classical example of cavitation that is equally hidden from general view, the marine propeller. By arresting all movement, It is now clearly seen that cavities originate near and stream away from the tips of the blades. The surface of this blade, from a propeller that has failed in service, shows localized areas of damage that are typical of cavitation. In a single screw vessel, the stern post and rudder are in the direct path of collapsing cavities from the propeller. These full-scale units show extensive damage with surface holes that measure several inches across. The conditions necessary to promote cavitation are easily created. Constant regard should be paid to its possibility in the early design stages of engineering equipment. Sharp bends or restrictions should never be allowed to impede liquid flow. The possibility of increases in liquid operating temperatures should be considered, and even the use of new materials showing resistance to cavitation. These, to quote Osborne Reynolds once again, are some obvious solutions to
a phenomena the secrets of which have been preserved by the deadening influence of familiarity on curiosity.